Hi everyone. The secret to unlocking human-level AI might very well lie within the minds of children. Their rapid mastery of complex motor skills and languages far outpaces the capabilities of our most advanced machine learning algorithms. What could be the key to this remarkable learning prowess? Can the core knowledge and brain architecture observed in infants inspire unprecedented advancements in AI? Keep watching to learn more. This video has 3 parts: child psychology, the special sauce, and relation to AI research. Part 1. Child psychology. I recently attended an academic AI conference in Vancouver called AAAI. It was a massive conference with, I think, 2,200 accepted papers. I can't believe the scale of AI conferences. And it had some very interesting invited talks. One of those talks was by someone from a slightly different field. Elizabeth S. Spelke is a professor at Harvard, and she studies child psychology, essentially. She's the author of a few books, including What Babies Know, and her research focuses on studying cognition in babies to figure out what makes humans different from other animals. And in particular, what are the bedrock categories of human knowledge, and how does knowledge in each category develop from its very beginnings? Here's a quote from her talk abstract. In their first years and with no instruction, children learn 1 or more natural languages. They develop a host of skills for moving themselves and manipulating objects. They learn the paths connecting places in their homes and the bonds connecting people in their social networks. And they deploy concepts of number, geometry, and causality that continue to guide the reasoning of adults. How children do this is a great unanswered question. So how does Professor Spelke study this problem? And apologies if I'm mispronouncing her name there. I don't remember the pronunciation. The experimental method that she uses in her studies is to do infant gaze tracking. Basically, she figured out that if an infant has learned something, then they're going to look at that thing for a longer time period. They're going to be more interested in it because we're talking about infants that are much too young to talk at this phase. So you have to use an indirect method to figure out if they've learned something. One experiment that the professor performed was to try to get infants to learn the difference between 4 objects and 12 objects. She had them look at 4 dots, for example, and then later was able to show that they had learned that because they would look more at 4 dots than they would at 12. And it's even multimodal. An infant can listen to a sound that occurs 4 times, and then later they'll be interested more in 4 dots. Basically, their brain is learning the concept of number. But what's really fascinating is that the researchers actually played the sounds, the 4 sounds, for example, or the 12 sounds in a row, to infants while the infants were sleeping. And even in that case, they actually were more interested in 4 or 12 dots visually at a later date. So in other words, even while they were sleeping, the infants were picking up information and learning it. There was another study that showed that babies are familiar with word segmentation before their birth. Word segmentation is basically the problem of you listen to a spoken language and you can figure out where the word breaks are supposed to be. Adults tend to learn word boundaries very slowly. If you've learned a second language, as I have been doing with Japanese, you'll know how difficult it can sometimes be to go, was that 1 word or was that 3? But babies and native speakers know word boundaries intuitively. This is even before they know the meanings of any of the words and before they know the grammar of the words as well. But there's enough patterns in the speech that they're able to figure it out. I actually have secondhand confirmation of babies being able to learn word segmentation. I have a friend who has English as her first language, but her mother spoke Spanish while she was a really young kid. I don't know if this was before or after her birth, but regardless, my friend was never taught any Spanish at all. However, when she tried to learn Spanish as an adult, her teacher said, "You have the ear of a native speaker." She was very good at reproducing exactly the right sounds, and I would guess had very little trouble with word segmentation. Well, again, this is probably because both Spanish and English were being spoken around her before she was born and as she was a very young child. But I suppose the Spanish speaking must have stopped at some point, and then she just picked up English as her only native language. Anyway, by using this infant gaze tracking metric, researchers were able to show that babies pay more attention to someone speaking their native language. And not only that, but they pay even more attention to someone who's speaking with their own regional accent. Slightly older kids would rather make friends with someone who sounds like them than looks like them. If someone is of the same race but has a foreign accent, for example, then they would not really prefer that person as a friend compared to someone of a different race but that sounds like they came from the same neighborhood. So word segmentation and being able to recognize your native language are really core parts of how infants and children interact with the world. And all of that learning starts even before the baby is born. Part 2, the special sauce. In her research and in her book, What Babies Know, Professor Spelke identified 6 core types of knowledge. These 6 core types of knowledge that are represented in babies' brains and adult brains are also shared with animals. They are places, objects, animate beings, social beings, number, and geometry. These 6 types of core knowledge don't really interact with each other and therefore potentially evolved independently. When an animal or human is engaging with one type of knowledge, then they don't use the others, and as soon as they switch to something else, their brain completely switches focus. And yes, plenty of animals exhibit all the signs of these 6 knowledge types as well. Presumably, they are what evolution deemed necessary to survive in the physical world. However, humans have a 7th knowledge type. This 7th type is language, and it's unique to humans, and it underlies all the language learning that happens within a baby's first year of life. We'll talk more in a minute about why animal systems of communication don't really count as language in this sense. When humans are learning language, doing so actually improves their object recognition. If you learn the name for something, it's easier for you to recognize it. It might improve number representation as well. This is my supposition, but I think the reverse is true as well. If you learn a different representation for a word or a concept that exists in your language, then that will result in a more solid understanding. It only seems natural. For example, recently I was looking at a map of Southeast Asia, which is the first time I've looked at it in great detail in a while, and I spotted where Myanmar was, which I didn't really know. And then when I started reading news stories about Myanmar, it was easier for me to remember because I had a visualization or a representation of what that country was. In fact, Professor Spelke talks about this 7th knowledge type or language learning as an actual cognitive catalyst. She thinks it's the secret ingredient for human cognition and what allows us to be so different from animals. Specifically, she thinks that human language is the catalyst that allows our numeric, architectonic, and social modules of our brain to all act in harmony. It allows them to join forces, swap ideas, and essentially engage multiple parts of your brain at once instead of just switching from one completely to the other. Here's a quote: "What's special about language is its combinatorial power. We can use it to combine anything with anything." Apparently, for example, children start integrating what they know about their physical environment and their navigational sense at around the same time as the age when they begin to master spatial language and think about what's left and what's right. Another paper I read points out that language has recursive machinery, and this recursiveness allows us to flexibly combine any concepts we like into complex, hierarchically structured thoughts. Yes, language, as in speech itself, is also hierarchical and contains very formalized structure, but the idea here is that that structure, that recursive property, can actually be applied to thoughts as well. As the paper puts it, compositionality is a key component of linguistically structured thought. So basically, the ability to think about something very small and very simple, and something else very small and simple, and combine them together into a larger composite thought is really what makes abstract thought possible. The legendary Chomsky even called this the basic property and argues that it evolved in humans because of the way that it allows us to structure thoughts rather than the way that it allows us to structure speech, although that was definitely a desirable side effect. So although Dr. Spelke is basically calling this 7th system the language system, I guess you could also call it the recursively structured system or the recursion and composition system or something like that. So what about language in animals? After all, some animals seem pretty smart. Like you can train a dog to push a button when it wants to get the humans to do something. And you have monkeys and chimpanzees and birds that all communicate with languages that seem to have reasonably large vocabularies. But this is the difference. Pretty much any concept that a human might want to think about can be expressed in language. But for all known animal communication systems, the animals can only express a small subset of the concepts that they can actually represent in their head. For example, honeybees have color vision. They can remember the colors of flowers that they visit, but the honeybee language, where they dance to communicate to other honeybees where to find food or whatever, allows them to communicate only the spatial location, the spatial direction and distance of that food, rather than the color of the flower that they're sending them to. And that's all the information that's actually needed for the honeybees to survive, which is good, but it means that the bees will never be able to scaffold thoughts upon thoughts and communicate to one another and build up a culture over time. Every honeybee has to start from scratch. So the special sauce is language, or recursive compositionality, or whatever you want to call it. Therefore, if you're trying to create really smart, like human-level AI, it makes sense to concentrate on those 6 core types of knowledge that other animals have and combine it with the existing language expertise. Because so far, most models skip over all of those 6 core competencies and they just head straight for the language, which is great because that's the most complicated one and the one that we interact with on a day-to-day basis. But it also means that if you ask a language model to do some reasoning, it has only the language capabilities there. It can't fall back on some spatial reasoning module to solve a geometric problem or whatever. Perhaps easier said than done though. Part 3, Relation to AI Research. One of the papers I saw at AAAI was called SyReLM, which I think stands for Symbolic Reasoning Language Model. The idea of this work is to take a small language model, they call it a frugal language model because it doesn't have many parameters, and get that model to offload some computations to a symbolic solver. This would effectively be taking one of those 6 core competencies that I talked about and fusing it with the language model. In this work, they focused on small language models with less than 50 billion parameters, because apparently numeric reasoning capability only starts to emerge once you exceed that amount. The idea is to take in problems that have an arithmetic component in natural language and convert them into a formal language, which you can then pass to a symbolic solver. The symbolic solver will use mathematically precise algorithms to figure out the solution and then pass it back up to the language model, which can answer the original queries. For example, you could imagine asking a language model to generate Python code, which then calls a symbolic execution engine. They did experiments with 2 main models, GPT-J, which has 6 billion parameters, and Vicuna, which has 13 billion. As the larger model, Vicuna can generate Python code, but GPT-J could only generate what they called pseudocode. Actually though, what they call pseudocode is essentially an assembly language that can do additions, subtractions, and other operations on variables that the LM defined. So the assembly language can look up variables from the original prompt, basically. Or if you want to be technical, it looks a lot like an SSA form inside a compiler. But anyway, how does this paper work? So first, they take the base model and they don't retrain it at all. Everything done in this work is based around fine-tuning. There's 2 main stages. First, they use LoRA, low-rank adaptation, to fine-tune the model to the formal language generation task. Remember, the formal language could be just Python or it could be their pseudocode language. Second, they fine-tuned the model to actually use the solver, and they incorporated a feedback loop to try to judge the quality of the formal language representation, including, for example, whether the Python code actually ran or not. The results were pretty impressive. For example, they showed a 30% in terms of absolute percentage improvement on one of the tasks, compared to the base model that hadn't been fine-tuned along with the symbolic reasoning engine. And that's a key point as well. This isn't just a system where they exposed a tool to an existing large language model, which is sort of how internet search gets exposed, for example. Instead, the symbolic reasoning is actually included in the fine-tuning of the model. Not quite during the training phase, because they just used a pre-trained model, but it's absolutely integral to the fine-tuning stage. In other words, during fine-tuning, the model would actually be generating some Python, running it, checking the output. This is a much deeper integration between the language model and the symbolic execution engine than just using it as a tool would be. And because all their work was done on small models that did not need to be retrained but just fine-tuned, this work was also very computationally efficient and easy for researchers to replicate. So I'm a big fan of this work. And it's interesting because it does represent combining one of those 6 systems along with the language reasoning capabilities. And I suspect there will have to be a lot more work like this in the future as we start to put together heterogeneous combinations of different types of reasoning modules. In fact, that was very specifically one of the ways to build AGI that was called out, and I talked about that in a previous video. There was another talk at the AAAI conference by the famous deep learning pioneer, Yann LeCun. He called out one of the main things that current AI systems are lacking, and that is hierarchical planning based on hierarchical world models. So what does that mean? Well, I've touched on that in the past as well by saying that large language models are essentially feed-forward neural networks. They can't think on something deeply for a long time because they don't really have cycles. They're not recurrent neural networks. That's one of the reasons that if you want an LLM to solve a complicated problem, you should use chain of thoughts and ask it to split its reasoning into small steps, because it's a lot more likely that the difference between one step and the next is going to be feasible for a feed-forward neural network than trying to get it to do it all in one shot. Another way of putting this is that the LLM doesn't have any planning capabilities. It can't plan ahead and say, oh, in step 5, I'm going to need this, so I should do this now. It can figure that out if you ask it to explicitly break down its reasoning into steps, but overall, the planning abilities are not very good. Even harder is a hierarchical planning ability. If you have a hierarchical plan, it means you have a top-level goal, a slightly lower-level goal, and even lower-level goals. And furthermore, the really low-level goals don't have to be worked out in detail in their entirety. For example, let's say my goal is to make a sandwich for myself, but I don't have the ingredients for the sandwich. So a lower level thing is I need to go to the grocery store to get those ingredients. And lower level than that is I need to figure out which direction I should go in order to walk to the grocery store, like which path would be best to take. But in order to do that, I need to figure out what the weather is to decide if I should wear a raincoat or just go out as I am. But in order to do that, I need to get up out of my chair and actually go to that room to check the weather. So as soon as I think to myself, wait, I need to make a sandwich, then that hierarchical plan can just form itself in my mind, and suddenly I'm standing up to go check the weather. And of course, I didn't have to plan out all the tiny steps in advance. Once I step into that other room and figure out what the weather is by, I don't know, asking my Amazon device, for example. I didn't have to map out in my head all of the individual steps I'm going to take all the way to the grocery store or whatever, because my brain can refine the plan as time goes on. Also important in this discussion is a hierarchical world model. You can only do planning at different levels in a hierarchy if you have a model of the world that is actually accurate at different levels. Hierarchical planning seems very natural to humans, but if you have certain conditions, then it can be really hard. For example, if you have ADHD, you might go out to see a friend and forget your jacket and get soaked by rain along the way. It's easy to get fixated on a goal and overlook the small things, or to live in the current moment and not really plan ahead too much. For ADHD, it can depend on the energy level that you have, whether or not you think about all the necessary steps. And I think it's a skill we have to learn and consciously practice as well. In fact, when a professor first asked me a problem, in other words, the equivalent of how do I get to the grocery store, I didn't know how to answer him. I was just like, well, you figure out the closest grocery store and you go there. But he was like, no. In programming, you first have to figure out, get up from your chair, take one step to the right, etc. And of course now, if I'm doing a coding task or anything like that, I'm engaged in many levels of hierarchical planning. So it will be interesting to see when AI systems can really engage in planning at similar levels or even more advanced levels, because I think that's one of the key components that's missing when you think about, can an AI system write code competently, for example. And the way this relates to everything else in this video is that you want hierarchical planning, but that needs a hierarchical world model. And I think it's difficult to have a hierarchical world model if you just have one reasoning component in your system that only understands language. But if you have incorporated one or more of those other 6 core knowledge systems, then I think it's much easier to have a hierarchical world model. My spatial reasoning capabilities can tell me how to get up out of this chair and over to the other room. My episodic or long-term memory can tell me which turns I have to take to get to the grocery store. My memory of what food tastes like can help me remember which ingredients I need to make my sandwich. And my number representation system can help me figure out if the grocery store is overcharging me for things or not. So it will be very interesting to see what AI systems will be capable of once they start integrating hierarchical world models, hierarchical planning, and more of those 6 core competencies that humans and other animals have as a sort of cognitive baseline. Finally, in conclusion, we talked about how Professor S. Spelke's work on studying child psychology has helped us figure out what babies know. We discovered that babies can start to learn about the number of items, they can start to engage their social muscles, they start to engage language learning and word segmentation even before they're born, and a lot of this learning even happens while they're asleep. The professor also identified 6 core areas in which humans seem to share a lot of similarities with animals, and those 6 core knowledge systems do not interact with each other. If the brain is focusing on one, then the other types of reasoning are shut off. Humans have a 7th reasoning system, which is what deals with language. And this 7th system is what enables humans to think abstractly, to reason, and to do far more than other animals can. In fact, this 7th system is a cognitive catalyst because it enables those 6 other core systems to actually work together. You can use some of this bit of reasoning along with some of that and combine it together with language. We're using language somewhat loosely here because structured thought, recursive thought, and compositional propositional thought is actually the mechanism that enables these different types of reasoning to be used together. And then once you have thoughts in a structured and whatever manner, then by using language processing parts of your brain, you can turn it into speech. In terms of AI research, we talked about SyReLM, which takes a really small language model that is not capable of numeric reasoning and combines it with a symbolic solver. This enables the combined system to solve arithmetic problems. It's directly analogous to one of those 6 core systems, the one that deals with numbers, getting combined with a language processing module. Finally, we also talked about hierarchical planning, which is something that existing AI systems like large language models are not very proficient at. Hierarchical planning seems possible once you have hierarchical world representations that could come about, for example, because you're representing more of those 6 core knowledge systems. So next time you walk out of the house without your wallet or your keys, you know that you can blame your brain's hierarchical planning system. If you liked this video, please check out this previous one I made where I talked about different definitions of intelligence and how we could think about whether an AI system is intelligent or not outside of the human lens. Well, that's all I have for today. Thank you very much for watching. Bye.